buffet, and you want to pick the top 2 dishes you like best. Easy, right? Now imagine you had to represent every possible combination of favorite dishes with just one tiny note in your pocket. That's basically what embedding-based retrieval tries to do. Squeeze all the ways queries and documents could be relevant into a single vector. This new paper shows there's a catch. No matter how big or well-trained your model is, the number of combinations you can represent is limited by the size of that vector. The math behind it, called sign rank, proves that some queries are simply impossible to capture if your dimensions are too small. To make it real, the authors built a simple data set called limit. Think queries like who likes apples, and even state-of-the-art models failed badly. The message is clear. Single vector embeddings have a hard ceiling.
Let's journey back 2 decades and see how information retrieval has evolved. In the early days, sparse techniques like BM25 were all the rage. But as neural language models advanced, we saw a shift toward using these models for retrieval tasks. They operate in a dense retrieval manner, compressing input into a single vector, or embedding. This has been a game changer, especially with new datasets. But the game is changing again. With benchmarks like QEST and Bright, models now need to interpret complex relevance for any query. Imagine finding a LeetCode problem with a shared subtask. It's not easy. This paper goes beyond just these benchmarks. It digs into the fundamental limitations of embedding models. What constraints do single vector representations pose? Let's find out. Now, let's explore some intriguing concepts. Imagine trying to map every possible combination of documents to queries. Simple? Not quite. Even top models struggle with this, scoring poorly on recall metrics. Enter the LIMET dataset, designed to stress test these models. Think of the embedding dimension like your color palette. Not enough colors, and you can't capture all the details. The authors draw from geometric algebra and communication complexity to establish a theoretical lower boundary for embeddings. There's a point where the document set size exceeds what's representable. They tested this idea empirically, showing limitations persist even with test data optimization. This is a wake-up call for rethinking embedding-based retrieval as demands grow. Let's talk about the advancements and challenges in embedding models. We've moved from simple text-only searches to sophisticated tasks with instruction following and multimodal representations. Pre-trained and multimodal language models, like Copali and DSE, are now key players. But with more domains and instructions, embedding models need to grasp full semantic meanings, not just keywords. This has sparked research into understanding their capabilities and limits. The journey to find nearest neighbors in semantic spaces has a rich history, with concepts like the Voronoi diagram. His mathematical underpinnings challenge our models, pushing the boundaries of what's possible. We're diving into the theoretical limitations of vector embeddings. The authors discuss approaches to the top-take retrieval problem, establishing a lower bound on dimensionality needed for embeddings. It's about figuring out how complex an embedding must be for specific tasks. Now, ever heard of sign rank from communication complexity theory? It's a way to place bounds on how embeddings function. The authors build on this by introducing a method for setting lower bounds using free embeddings. They then talk about the representational capacity of vector embeddings. Queries and documents are mapped to vectors, and relevance is captured by their dot product. The goal is to ensure relevant documents score higher than irrelevant ones. 2 definitions related to matrix ranks help determine the minimum embedding dimension needed to maintain relevance order. It's all about effective sorting and prioritization of documents. Here, we delve deeper into the mathematical groundwork. We start with globally thresholdable rank, which finds a single threshold to separate relevant from irrelevant in a matrix. Think of it as setting a clear pass-fail line. We explore the relationship between representational capacity notions. Row-wise ordering and thresholding are shown to be equivalent. Proposition 1 formalizes this, linking these concepts. Then there's sign rank, used to match sign patterns between matrices. It's a complexity measure for replicating matrix structures. Proposition 2 provides bounds on matrix ranks, explaining how they can be manipulated and what that means for separating relevant from irrelevant data. This framework helps us grasp embedding limitations precisely. Let's look at the implications of this mathematical framework for vector embeddings. It provides dimension bounds needed for specific retrieval tasks. Remember sign rank? It's crucial for determining embedding complexity. For any fixed dimension, some binary relevance matrices can't be captured due to high complexity. High sign rank matrices require sophisticated embeddings. They discuss using gradient descent optimization to find sign rank upper bounds, helping determine necessary dimensions. They introduce free embedding optimization, where embeddings are optimized without natural language constraints. This showcases the best case optimization scenario, using techniques like gradient descent to push boundaries and highlight embedding potential when given full freedom. Now let's get empirical. The researchers explore the critical endpoint where optimization fails due to dimensionality limits. They increment document and query numbers to find this breaking point. They focus on small document and dimension sizes because combinations grow explosively. Using polynomial regression, they extrapolate results to larger scales, showing large-scale web tasks are challenging with existing dimensions. Look at Figure 2. It plots critical values against dimensions, illustrating how dimensionality must grow for complex tasks. Shifting to real-world datasets, they question practical applications of theoretical insights. Existing datasets, like QUST, have limited queries, barely scratching possible combinations. This sets the stage for understanding the gap between theoretical potential and practical application. Let's talk about the challenges of creating evaluation datasets for large corpora. Developers, facing computational limits, often choose fewer queries, leading to incomplete combinations. Queries like novels from 1849 or George Sand novels involve complex logical operators. Some tools allow such queries, but complexity isn't always practical. The authors create a dataset evaluating all top ESC set combinations, focusing on fewer documents to highlight representational difficulty. The LIMIT dataset uses latent variables for queries and documents, with attributes like preferences for Hawaiian pizza. It's designed to be simple, with minimal user attributes and straightforward queries. They use 50,000 documents and 1,000 queries for significance while remaining manageable. A Krell matrix instantiates attributes, aiming for density with all combinations. Random attributes are assigned to queries, with documents named using open-source lists. This setup emphasizes the complexity of representing all combinations, providing a robust test for models. How do state-of-the-art models handle the LIMIT task? Despite its simplicity, many models struggle. Look at Figure 3. It plots recall scores against embedding dimensions. As dimensions increase, performance improves, but the task remains challenging. They discuss models like GRIT-LM and Prompt Retriever. Models trained with diverse instructions perform better, perhaps due to broader embedding dimensions. Lexical models like BM25 excel, thanks to higher dimensionality. Even multi-vector models face challenges, showing more vectors aren't a magic fix. Matryoshka learning struggles unless trained with MRL technique. The results highlight embedding dimensionality's importance for performance, questioning whether alternative architectures could offer better solutions. Does domain shift affect model performance on the LIMIT task? Check Figure 4. Even with 46 documents, models struggle for high recall scores. Increasing dimensions doesn't hit recall targets, though BM25 performs well. To explore domain shift, they test if training on a similar dataset improves performance. If unfamiliarity is the issue, this should help. Otherwise, only training on the test set would allow models to learn specifics. Look at Figure 5. Using an off-the-shelf embedding model on training and test sets shows minimal improvement with similar datasets, suggesting the problem isn't domain shift. Instead, models perform better through test set overfitting, echoing free embedding experiments. The conclusion? The issue's complexity lies in model limitations, not just domain differences. Let's dive into query relevance patterns, effects on model performance. Figure 6 shows results from the LIMIT dataset with various patterns. Dense patterns, using maximum combinations, challenge models like GRIT-LM and E5 Mistral, dropping scores dramatically. They experiment with 4 Krell patterns: random sampling, cycle-based, disjoint, and dense. Dense patterns yield lower scores, highlighting complexity. The discussion shifts to LIMIT scores and BEIR benchmarks correlation. Figure 7 shows no strong link, suggesting different benchmarks test different capabilities. This underscores dataset structure's importance and its impact on evaluating model performance. It highlights dense patterns, complexity, and the need for diverse evaluation methods to gauge model effectiveness. Let's explore alternatives to traditional embedding models, given their limitations in representing all document combinations in top-talk sets. Even as dimensions grow, they can't handle every combination, especially at scale. Cross-encoders are one alternative. They aren't ideal for initial retrievals due to computational demands, but excel in re-ranking tasks. The GEMINI 2.5 Pro model, for instance, handles all queries in one pass, overcoming some embedding limitations. Multi-vector models, using multiple vectors per sequence, show promise on the Lemma-T dataset, outperforming single-vector models despite less usage in complex tasks. Sparse models, lexical and neural, leverage high dimensionality to scale effectively. Models like BM25 outperform others by managing more combinations. However, applying them in areas like instruction following remains a challenge, pointing to future research needs. In conclusion, the Lemma-T dataset reveals embedding models, struggles with certain tasks, highlighting the need for more expressive retrieval architectures. These findings encourage exploring alternative models to address gaps left by traditional embeddings. Thanks for joining us today. Happy exploring together!